A very good day, everyone. Today, we are going to present and share our research study regarding the techno-economic analysis of renewable energy with the energy storage system, we call it ESS, in improving the reliability and also the stability of power system for the Malaysian prospects. We are from the group of four. We have Chia, Desmond, Govin, and me, Jaden. As we are living in a fast-paced technology developing era, the current global energy demand is actually increasing rapidly. And the electric production in Malaysia is actually still mainly based on the fossil fuel and also coal-based processes. So this will then cause undesired environmental impacts such as greenhouse gas emission and also air pollutions. Therefore, people nowadays are looking forward to use renewable energy to generate electricity in order to achieve a sustainable energy development. And the ESS are crucial for improving the overall system stability. And also, Malaysia actually targets to achieve the renewable energy transition, and this target is guided and supported by the two roadmaps, which are Malaysia Renewable Energy Roadmap by RER and also the Energy Transition Roadmap NETR. Our research study aims to analyze the technical performance of different renewable energies with the integration of various ESS options, and we evaluate the economic feasibility using the LCOE, LCOS, and LCOH. Next, we also assess the impact of ESS integration on the reliability and stability of renewable energy systems. One of our goals is also to compare the suitability of different RE for the small scale and large scale application in Malaysia, and also environmental analysis will be conducted. Lastly, we will make an effort to provide the insights for Malaysia's future energy planning and also development. In our research study, we have selected three types of renewable energies, which are solar, hydropower, and also hydrogen energy. We have conducted a lot of literature review and also research on the energies and two ESS options for each of them. For solar, we have battery energy storage system, BESS, and also supercapacitor. Followed by hydropower, we find out the difference between pump storage hydropower and the seawater pumps storage hydropower. And lastly is the hydrogen energy. We have done research on compressed hydrogen gas tank and also metal hydride storage method. These ESS options are then further analyzed to choose the most suitable one for each renewable energy.
Thank you, Jaden. So first, three renewable energy and ESS combination were selected for comparisons. The first combination is the solar PV with the battery ESS, which is the BESS. So this combination was selected because BESS has high efficiency, fast response, and strong compatibility with solar PV systems. So it can store excess solar energy generated during the daytime and supply electricity during periods of low solar generations. In addition, BESS support functions such as backup power, peak shaving, and load shifting. The second combination is the hydropower with the PSH. So PSH was selected because it is a mature and reliable energy storage technology with large storage capacity and long storage durations. So it is widely used for grid balancing and peak load support, making it an important technology for renewable energy integrations. The third combination is the hydrogen energy with compressed hydrogen gas tank. So this combination was selected because hydrogen storage provide long durations and seasonal energy storage capability. So it also has strong future potential for supporting clean energy system with high renewable energy penetration. Next is the methodology framework. So after come out with the best ESS combination for each renewable energy, Two application scenarios were then defined. Scenario 1 represents the small-scale application, while Scenario 2 represents the large-scale application. So the selected system were evaluated through technical performance analysis, reliability and risk assessment, economic feasibility analysis, and comparative analysis. Finally, the majority of future prospects of the selected renewable energy and ESS combination in Malaysia were studied. Next is the evaluation criterion slide. So two application scenarios were considered in this study. The large-scale scenario represents the centralized system connected to the transmission network for national grid application with capacities ranging from megawatts to gigawatts. Meanwhile, the small-scale scenario represents distributed systems such as residential, commercial, and isolated microgrids with capacities in kilowatts. Several evaluation criteria were used to compare the selected ESS technologies. So these include efficiency, which refer to the proportional of stored energy that can be retrieved, storage duration, economic feasibility, and reliability and risk assessment. Next is the economic evaluation. Economic analysis was carried out using LCOE and LCOS. LCOE represents the total cost of generating electricity over the project lifetime, while LCOS represents the total cost of storing and delivering energy throughout the system lifetime. The economic analysis considers both capital expenditure and operational expenditure. CapEx includes equipment and hardware costs, development costs, grid connection, construction, and logistics. OpEx include operational and maintenance, insurance and security, as well as regulatory and compliance costs. A discount rate of 7.5% was also applied in the economic calculations. Overall, this methodology provides a systematic approach to compare the technical, economic, and operational performance of different energy storage technology and determine the most suitable solution for renewable energy application in Malaysia. Thank you.
Thank you, Desmond. Now I will compare the technical and economic performance of three renewable energy storage systems. In terms of round-trip efficiency, solar PV with BESS achieved the highest efficiency at around 83%, followed by PSS at 75%, while hydrogen storage is much lower at approximately 33% due to conversion losses. For storage duration, batteries are suitable for short-term storage of several hours. PSS can store energy for days to weeks, while hydrogen is ideal for seasonal storage over several months. Economically, PSS is the most cost-effective option with the lowest LCOE of 3.37 cents per kilowatt-hour and LCOS of 5.93 cents per kilowatt-hour. Although hydrogen has relatively low hydrogen production costs, its overall efficiency remains a challenge. Next, I will discuss on reliability and risk assessment of these three renewable energy with ESS. Solar PV with BESS offers fast response time, grid support services, and mature commercial technology. However, battery degradation and thermal runaway risk can reduce lifespan and safety. Hydropower with PSS is considered the most reliable technology due to its operational lifespan exceeding 50 years and commercially matured. Its main limitations are site dependency, sedimentation, and environmental impacts associated with reservoir. Hydrogen storage provides very long-duration energy storage, supports seasonal balancing, and zero carbon emission. However, challenges include hydrogen leakage, high-pressure storage requirements, and limited long-term operational experience. By comparing those renewable energy and ESS, it has been found out that for deployment scale, solar PV with BESS is recommended for residential and commercial applications, while PSS is most suitable for large-scale national grid. As in small-scale application, only short storage duration is required since charging and discharging can happen frequently, while in large-scale application, longer storage duration is required with moderate efficiency to supply the load immediately. After doing research, we have found out that there is lack of information related to deployment of hydrogen system. In Malaysia, rooftop solar adoption is supported through NEM, and LSS programs, whereas the Pakundan demonstrate the strong potential of hydropower and future PSH deployment. After choosing the best solution, the environmental benefits and impacts of those ESS are analyzed. Solar PV with BESS significantly reduces greenhouse gas emissions compared to fossil fuel generation. However, most environmental impacts come from panel and battery manufacturing processes, particularly silicon production and battery disposal. Hydropower with PSH has one of the lowest life cycle greenhouse gas emission among large-scale storage technologies because it relies on mechanical water storage instead of chemical materials. Nevertheless, dam construction can affect ecosystems, water quality, and sediment transport. Overall, both solar PV with BESS and hydropower with PSH produce lower life cycle emissions than conventional fossil fuel electricity generation. Next, I will pass the floor to Govin.
Thank you, Chi Young. So now I'm going to talk about the future prospects and development of solar PV plus BESS and also hydropower plus PSH system. So firstly, solar PV BESS is expected to grow due to declining battery costs and also technological advancements, even though the battery capacity will degrade about 2% annually. Its future performance was assessed over a 10-year period. On the other hand, hydropower PSH is a mature large-scale storage technology with a lifespan up to 150 years, and its future performance was evaluated over 100 years using sedimentation analysis based on the Churchill and Broun methods. So, the future performance modeling for solar PV plus BESS was done by first calculating the state of health of BESS, which was then used to calculate the usable energy after aging. So these are all the parameters that we used in the analysis for 10 years, where we found that the state of health of BESS dropped from 100% to 80% across 10 years, while the usable energy of BESS dropped from 8 kilowatts hour to 6.4 kilowatts hour over 10 years. The drop in this usable energy and state of health is because of battery degradation, which is caused by electrochemical aging processes. Let's move on to the future performance modeling of hydropower plus PSH. As we can see from this graph here, the impact of reservoir sedimentation on the long-term energy storage capacity of pump storage hydropower system is very small. The Churchill and Broun methods predict a total reservoir storage capacity reduction of 1.6% and 1.8% respectively only after 100 years of operation. Using the Churchill and Broun methods just now, we can then see the effect of sedimentation on the energy storage capacity across 100 years. As we can see from this graph, the energy storage capacity decreased from 6.803 times 10 power of 6 megawatts hour to 6.694 times 10 to the power of 6 megawatts hour when using the Churchill method, and 6.681 times 10 to the power of 6 megawatts hour when using the Broun method across 100 years. This graph shows that sedimentation does affect the storage capacity for hydropower, but very minimally. Moving on to the next slide, where we are going to look at the policy and standards governing solar PV BESS, hydropower PSH, and hydrogen storage systems. These frameworks provide requirements for safety, performance, operation, and also system reliability, which will support the sustainable development of renewable energy in Malaysia. To conclude, solar PV plus BESS is the most suitable system for small-scale applications, while hydropower plus PSH is more suitable for large-scale applications. Even though hydrogen plus compressed gas tank has a very high storage duration, its efficiency is the lowest out of all three systems. Hydropower plus PSH was found to be the most economically feasible because of the lower LCOE and LCOH per kilowatt hour. That is all from us. Thank you very much. And here is our references. Thank you.